And I am missing one lecture, which we'll just do like this. This one. Okay, so I hope you had a nice reading week and you did some reading. It seems like we're only seeing each other every fortnight, but from here on in, it's every week until the end of term. So it's a little bit more of a push. Thank you for submitting A2. We're accepting late submissions up until this Friday. And then once this Friday hits, we'll start marking it. How did it go relative to A1? Double thought, like harder or worse or about the same? Flat? That's good. Because you should be getting better with Haskell, but also the problems are getting a little bit harder. So we'll see how the last one's going. So the last assignment's going to be deployed this Friday. Do you want more written work or less written work? Less written work. Okay, so they'll only have you do like maybe 1 or 2 proofs. It seems that mostly the like automated work is being done really well. So it's better that like I turn up that weighting. Because again, I want everyone to do well in this course. In American cultures, it's traditional for the higher level courses to be easier to get higher marks somehow. Don't ask me why. Okay, so today we're going to be talking about monads. Has anyone ever heard this term monad? It's kind of like a meme on the internet that like no one is able to actually explain what a monad is or how to use one, which puts me in the precarious situation of having to talk about it for like the next couple hours and try to explain it to you. It's not as hard as people say. It's just that you need like all of the background knowledge that we've been building. So it's a monad is just going to be another class instance. It's just going to be another class from which we can make instances of, like the same way that a type can be a functor instance, or it can be an applicative instance. It can also be a monad instance, which means I just have to tell you what operation monad instances have and what rules those monad operations have to satisfy. In the ECP, I actually said I was going to make today's lecture like twice as long, but I must have been like hallucinating or something, because like I checked my previous lectures from the past 2 years. Last year, I was like really rushed. And then I got a lot of comments that like this lecture is rushed. So when I was reflecting on like how to make changes for this year, I thought, okay, I'll make this lecture longer. But in the first year, this lecture was short by like a lot. So I don't know. So I'm just going to revert back to like the original schedule where we're going to do monads and state monads today. And if we run out of time, I'll just allocate some of next lecture to it. But so the lecture schedule is going to be updated somewhat. It's not going to be overly bad. Okay, so let's just take just review what we've covered for the last couple of weeks, because those last couple of weeks have spanned the last 4 weeks. So we've started trying to generalize all of the things. So any of the patterns that we've been using, we've been trying to make higher order functions to replace them. The first sort of category that we developed was something called a functor. So something's a functor, right? So f is a functor when, and remember here, f is some type of data type. You give me a function that can go from A to B. You give me structure over A, and then I return to you something with structure over B, right? So the important thing here that this was a structure preserving operation. That is, we took this function, we went inside the structure, manipulated the inside of the structure, and then left, right? So if this was a list, the list would have the same length. If this was a tree, the tree would have the same number of nodes. It was a structure preserving operation. We then went one higher than this to do something called an applicative, which is a little bit weird, but an applicative, so some type is an applicative when that type also is an instance of a functor. So this f has mapping already, and we have to apply have 2 more operations. The first of which is pure. That is, given something from A, you tell me how to like put structure over it. So if this was like a list, maybe you give me a number and I return to you a list with 1 number in it. If this was a maybe data type, perhaps you give me A and I return just of A. And this, what I was calling in my previous lectures, applicative functor. I'm not actually sure that's how you're supposed to call this, but I can't figure out how to actually say this. So I'll just call it the applicative functor. You give me some type of function, but the function has structure surrounding it, right? So this is like a list of functions. And then you give me a type A with structure over it, and then I return to you something with B with structure over it. So the applicative was kind of weird. The list applicative, for example, works like a Cartesian product, which is kind of bizarre. I guess for your assignment 3, I'm going to be having you prove a different applicative for lists. Okay, so what's the punchline of today? What's a monad? Well, a monad is just a type M, which is also an applicative, an instance of an applicative, which also means it's an instance of the functor, which provides the following two functions. And these functions also have to satisfy rules. So the first function that we have to have is called return. And it takes something from A and it just puts structure over that A. What does that look like? Line 9. Yeah, it's like exactly like 5. So they're discussing actually removing this from Haskell because, for one, it's because M's already an applicative, you already have pure. So return is not, it's redundant. Why should we have to define this again when in every case it's pure? And it's a word that has loaded definition. Like we use this in imperative programming to mean something like totally different. Like I'm sure when all of you started off in Haskell and did some searching online, you saw pieces of Haskell code with do's and returns and were like, yeah, I know what those are. But it turns out those do's and returns are like totally different, right? So for those reasons, return may actually be leaving the party. But the important thing is this operation here, which is called bind, which is deliberately named, right? If you remember all the way back to week 1 when we're doing lambda calculuses, one of the operations that we could do on a lambda calculus was bind them, right? So this is the bind operator. So let's study its type signature. It's you give me a type with structure over it, and then you give me this funny function, which given A gives me back something from B with structure over it, and then I can give you something with structure over it. This looks bizarre, and a lot of what we're going to do today, like we don't really need a monad, right? In fact, many people in Haskell don't use the monad. They only use up to applicatives, right? Because you can do everything using the applicative form, but like we will be using monads, but we really can't understand like their true purpose until next week when I introduce IO. Can you believe it? We're like week 9. I still haven't done print hello world. It really will take the last lecture to do this properly. We have already used data types that are monad instances, right? The same way that we had used data types that were already functors and applicatives. Either is a monad instance. List is a monad instance. Maybe is a monad instance. Arrow R, so like these are all functions mapping from R. Like that would be a monad. And we've been actively avoiding this monad instance, the IO monad instance. But this is the reason we're showing up today. So because next week I'm going to say, let's introduce an IO type, and that IO type is a monad. So let's talk a little bit more about this bind operator. So it's actually in the system. This is not something theoretical, or it's not only theoretical. Go away. Wait, go away. What is this? This is Python code. That's something else. Okay. Let's just go into Haskell here. So I should be able to get some typing information for this bind operator. Right, so the bind operator is given something that's a monad, M, give me something with structure over A, a function that takes you from A to something with structure over B, and return something with structure over B. Right, so it's in the system. We use the bind operator to reach in and extract the contents of something with structure, right? So you'll see this in its operation, but this is going to be important. So far we've been reaching into structure where we could have also done pattern matching to get the stuff out. What we haven't yet dealt with is data types which have structure, which don't admit pattern matching. Right, so we're going to need some way of like reaching into types with structure around it without having to do pattern matching. And this is exactly what this bind is going to allow us to do. So for example, if I wanted to increment just x, right, to get just x plus 1, how could we do this? Well, let's go out to here. Let me spin up a function. And let's discuss all the ways that we could increment to just. Oops, where is it? Does anyone else use VS Code here? You find it's getting like way slower? Like I've been getting a lot of like kernel panics. It's okay. So that's good news. Maybe I just like corrupted my local environment. Anyways, okay, so here's the goal. I want to just increment just 1 to get just 2. And let's think of all the ways that we have to do this. Okay, so I want to come up with a function increment, a maybe increment, which takes a maybe integer to a maybe integer. Okay, so the most basic way of doing this would be what? Maybe increment just x. Yeah, it is just x plus 1. And then maybe increment, oops, that bracket doesn't go there, it goes here. Of anything else is nothing. Okay, so that's the first one. Whoops. Maybe integer. Okay, so I can maybe increment just 1 to get just 2. Okay, so that's style 1, right? The most primitive type of Haskell. What other ways can we do this? Well, yes, F map. Yep. So I could just do something like given this maybe x. Oh, I also have to say, look, this works with nothing. Cool. So I'm just going to take plus 1 and map it to maybe x. That should also do it. Maybe increment just 1, get just 2. Maybe increment nothing to get nothing. Okay, so now let's do this with a bind. So I'm just going to get the type information for bind. So how can I do this with a bind instead? So the first thing I need to do is have a function that given something, I need some function that given a returns something with structure over it. So that's going to be something like this. Okay, let's just work in here. Oops, I need that. So I want to take something from just 1. That's going to be this. And then I want to bind it to this, which I want to say take plus 1. Oh, no, take lambda x and go to just x plus 1. And that should work. Okay, just by like satisfying this typing. So the way that I sort of conceptualize this is I imagine like this operator is kind of like a shove operator, like force this, like I'm saying, take this and like shove it into this function that I'm giving. It doesn't quite fit, but if you like push it really hard, it will work. Okay, I know that sounds kind of weird. So, but we're going to see some structure come out of this. Let's go back to my slides and see what I'm supposed to do. Okay, so let's now do this instead. Suppose I want to add 2 maybes. So this is going to be a maybe integer to a maybe integer to a maybe integer. And let's do the same type of steps here, like the different ways that we can actually implement this. So I want to maybe add just x to just y. That's going to be just x plus y. And then everything else is going to be nothing. I have to credit this fellow over here. was sort of pointing out to me that we don't really have to do this. Right? Because really, like, all of those cases are handled if we match these two jests. It's true, but only because maybe it's like a really primitive type of error handler. If we were doing eithers, remember that either actually has to return the appropriate error. We would have to delineate these edge cases, but it is certainly the case that it's going to work here. So let's just try to see if this works. Just one, just two. Whoops. What have I done? Nothings. Okay. Whisper sweet nothings into my ear. Okay, just three. And you can see that the error handling still works. Cool. How can we do this using functors and applicatives instead of doing this? Anyone know? Yeah, it takes a little practice, but it's going to be something like this. Maybe X, maybe Y. I want to take the functor applicative of these two. And then what operation do I want to map over that is addition. All right, so that's going to work. Maybe add just one, just two. Oops. To get just three, and the error handling will work. Okay, so now I'm going to do this with, again, the bind operator. So it's going to be a little bit tricky, because what I want to do is I need to take X. Let's hope I can do this. Everyone pray. Need to take X, and this needs to go to a function which takes Y. Oh, no, not binding. I need to take MX, and I need to bind that to a function X, which goes to taking M of Y and binding that into a function that takes Y to just X plus Y. Jeez, before I start trying to explain this, dear Haskell gods, thank you. Okay, so let's see if this works. Cool. Cool. Great. Okay, so I heard some grimaces over there, which are appropriate. This is ugly as, right? We don't like coding like this. Is basically has no meaning. I had even trouble coding it. Okay, but let's make some amendments here, and perhaps we can try to start getting structure out of this. First thing I want to say is that because of the rules of evaluation, I can actually remove all of those brackets. So we're still in business, and this is still working. Okay, the other thing I'm going to do maybe is move some of this stuff around to get this. Right, so MX gets shoved into a function which takes X to a function which takes MY and shoves it into a function Y, which goes to just X plus Y. Since I'm in a monad, what can we replace this with? Yes, sir. Bingo, bingo. Still working, right? Because the return is literally just in this case. What is this beginning to look like? Yeah, it looks like kind of the do notation. So I'm going to introduce a little bit syntactic sugar now, right? Because this is kind of an ugly statement. So I'm just going to spin up another function. Let's just call this mad prime. So if you put do here, what this is going to say is, hey, I want to use special notation for binding because the binding notation is ugly. And the notation lets you take this because I don't want to have to keep spinning up anonymous functions into anonymous functions. So what I can do here instead is use this notation, which I'm saying is like identical to the previous notation because it's syntactic sugar, right? Python just says, oh, I see, Python. Haskell sees this and it just says, I'm going to swap out for like the previous thing. So this didn't violate our functional purity, right? It's functions, right? The funny thing about these binds is that it's actually allowed us to sequence operations. The X happened before the Y, just by the way we still have sequencing in terms of like the order of evaluations. If I have a function which evaluates something from a function to a function, that is simulating sequencing. That's why we say that these do monads give us brief imperative programming blocks, right? Because these are sequenced. Now, just run this to ensure, or to say, look, this is valid Haskell code. And this is how we can read statements like this. Give me a maybe X and a maybe Y. Now do the following things. Reach into the maybe X and pull out X. Reach into the maybe Y and pull out Y. Add them together and return them, by which I mean put the structure back in. So what is this allowing us to do? Given types with structure around them, this gives us a code region where we're permitted to go inside the structure and make changes. But we have to wrap everything up again before leaving. And why will this be important? Well, because we may not always be able to do pattern matching to get something out, right? Next week, that's what IO is going to be. It's going to be a really strange pattern match, which we can't pattern match out. So the do notation will allow us to jump inside IO and make changes. Okay, so let's see if this is even working. So just one, just two. Line 4 is, why is it getting angry at me? Oh, I can't have a return here. This has to be just. Okay. Okay, let's try this. Just 3. Let's try this. Cool. Both nothings. Right, so you see how like this is also handling all of the error lifting for us. Would this have been useful for A2? Your evaluate expression, you should do it again now using the do monad. Yeah. That's a good point, actually. Okay, hold on, let's see. Because it didn't complain. So what was the error I was getting? I have to be able to generate it again. Or maybe I just didn't load. Okay. It does work. This does work because all that is required to use return is for the data type that we're using to be a monad, and maybe is a monad. Right. So, but anyways, it'd be strange to use return without. Well, in fact, pure would have also worked here because it's also an applicative. It's just not very good style to do that. Although, okay. What happens if I remove this? What do I have a function that does? Or yes. Okay, so why don't we just take a step back and try to get the typing information for this. And all of it. Take this as practice take it as exam practice. What is the type of this function? And as well as the class instances that need to be derived. Yeah. Okay, so yes, I'll repeat that. So because there's a plus here, whatever X and Y are have to be from a number instance. Like we need plus. And because there's a do here and a return, but either would mean this, these have to be from a monad, because I'm saying use some of the monad, like use bind is effectively what this is saying. So let's take a look at this. You are correct. It's something that's a monad M and a number B. And then I get a function which takes a monad over B and a monad over B and a monad over B. So will this work? Is either a monad? Oh, sorry. It would work, but this is better. Cool. Because left are for errors. Okay, so let's walk through this again. So MX here is just going to be something from the either data type. I'm going to say reach into that either data type and pull out what's inside. reach into that either type and pull out what's inside. So in this case, it would be right. So let's see, what have we done? Oh, isn't that cool? So we didn't actually write a function that's able to add maybes. We wrote a function that's able to add any two things which are from the same monad. This is like a lot larger of a category of stuff that we've just solved. Okay, will this work? Well, if the monad was set up properly, you would expect errors just to be sent up the chain. Okay, what about stuff like this? Is the list a monad? Yes. Anyone able to predict the outcome of this? Okay, cool. So okay, I'll just remind you what the list duplicative is. Oh, I can't actually. Okay, hold on. I'll have to do this. So given that, what will this be? Yeah. But see, we have like one adding function that's just going to work for all of the things that are monads. And this is the true strength of Haskell, right? We don't have to define an addition operator for like every new data type. It's just like, no, it just comes out of box. Like provided that your data type has these rules, these operations, and can do the following things, then here's your add operator. Just like a really powerful idea. Yes, sir.
Maybe also that either monad has been set up with raised left side.
Yeah, left is error because right is right and left is incorrect. Yeah. Yeah. No, it would raise the error. So if I did right two, because like what should these two sum? Like what is right two plus left error? You would expect left error.
If you switch like left, if you wrote left two and then right error.
I don't think that's gonna type because this means that like the thing that's right that right's putting structure over has to be from a number instance. This is a string. Like, don't think left and right as like where they are in the input, right? We have a union of two types. And like left are all the errors, union with all the non-errors, right? So that's the left and right, not the order. Yeah, because like recall that the either data type allows us to take the union of two types. So we have A or B. One of the types is on the left, one of the other type is on the right of that. And it just so happens that we designate everything in the left set to be the all of the errors that you can possibly throw. Because of the agreement that the word right is synonymous with correct, which is the antonym, the opposite of the word correct. You know what I mean. Screw these guys for trying to fluster me in the morning, right? No, I'm just joking. Any of you follow ice hockey? No? My team is the Toronto Maple Leafs, and they're cursed. They haven't won the cup for over half a century, 52 years, 53 years. They haven't made it out of first round for 19 years, and they made it out of the first round 2 days ago. And I am, oh man, am I happy. There's still two more curses though. We can't beat the Boston Bruins. They're our nemesis. And then the fact that we haven't won the cup for half a century. So we made it out of round one. Round two, we have to face the Boston Bruins, who not only are our nemesis, but have had the best regular season out of any NHL team ever in the history of the NHL. But you know what happened to the Bruins yesterday? they were eliminated by the worst team in the championship. So we don't have to go up against Boston Bruins in round 2. We have to go up against the worst team in the championship, right? So second curse gone, right? So I know you guys aren't interested in this, but my 1001 class, I told them if the Leafs won the championship that I'd give them all 7. So they're like really keenly following this now. But like none of them bothered to check when the NHL championships are done, because it's well after I assigned their grades. They're just thinking to the next step. So don't tell them. It'll be funny once they realize this. Okay, let's move on. But go Leafs, go. Okay, so that's just everything I said, but in slides, so you can have it. Right. So this and this are identical. Right. So when we answer, like if I ask you, is the do notation like still functionally pure? You say yes, because it's just like a composition of binds, and those binds are functionally pure. What's the big deal? Can't we accomplish this with applicatives and functors? Surprised none of you asked. Can I get rid of that? Yes, we can. But our example wasn't really one where self-computation could fail. So let's look at let's look at a problem where self-computation can fail and show that this do notation is really helpful. This is exactly what I instructed Vladimir to write for assignment 2. I said, figure out some type of expression which they have to evaluate where sub-expressions can fail, right? Because then you have to sort of be careful with. I would love to talk about the solutions for those assignments, but we still have till Friday to accept them. But next week, I'll go over some solutions. Which solutions do you want me to go over for next week from your homework? Functional. I could do all of them. It's just sort of, it would be eating into the time for other stuff. That's why I want you to order prioritize them. Yeah. Okay, I'll do both because it was honestly just a handful of lines, especially if you use the applicatives that we learned that week. Okay, so I'll try to do all. Those 2 will be the top of that priority. I can show you how to do blockus too, just to show you that that wasn't overly difficult if you chose the right way of looking at it. And did we give you anything else? Oh, shortest. Okay, but that was just kind of a fun one. Well, fun for us to watch. You panic. Okay, so let's try something more sophisticated. What's our example? Because it'd be great if I could just take your homework example now, but could I do that? If I solved your homework using a monad, no. Because I could say, look, then don't submit a monad, or I know you would have cheated, but we'll just wait till next week. I promise I'll do it again. So we'll do this one instead. So suppose I have a data type for expression, which can have values which are integers or division expressions, right? So constrain yourself to arithmetic expressions with numbers and division. So what can go wrong here? Yeah. Can't divide by 0. Can we satisfy? Okay, so let's just try to start implementing this and seeing the stuff that can go wrong. Okay, so I have this. What did I say we need to do? Let's write an expression for evaluating this. Okay, so we want to eval things that are expressions into what? I don't know, integers? Maybe integers? All right, let's do maybe integers. And let's use integers instead of these names. Okay. Or maybe, should we do maybe integers or integer? What do you want to do? Should our evaluations return a real number? Or I guess if these expressions can fail, then it has to be a maybe integer. So I'll leave it like this. Okay, so what is the evaluation of this? The easy one. X. Oh, just X. Yeah, it's there, just X. Okay, so eval now an expression. So the other expressions are going to look like this. So divide expression 1 with expression 2. So how's that going to look like? Well, I want to do something like divide, evaluate expression 1, evaluate expression 2. But like this already won't type, right? Why won't it type? Oh, no, this will be okay, I think. No, it won't type. Because the divs have to take expressions. Yeah, and these evaluates are returning maybe integers. So you have to be more clever about what we're actually returning. Okay, let's go return to the slides. What did I actually want to do? I wanted to return an integer. Okay, so let's just do that instead. So if this happened like this, okay, so I want to evaluate a function that returns an integer instead. This is not gonna work, but that's sort of like the point of like this example. That means the division is going to be like the regular division, right? So I'm saying, okay, here are two. I want you to divide expression 1 by expression 2. And I say, go evaluate expression 1. Hopefully I get an integer back. Go evaluate expression 2. Hopefully I get an integer back. And then we'll divide them. This should work. No, it shouldn't because I can't spell. Oh my Lord. Okay, so let's try evaluating div of value 4 over value 2. Okay, but that error. So we want to fix that error. So what's the first thing I need for this to fix it? Yeah. Yeah, I need safe divide. So I'll just make safe divide, which given two integers returns maybe integer. And that's going to be something like this, right? SDiv of anything in 0 is nothing. Otherwise, it's x divided by y, which should be just div x and y. Okay, so can I change this to safe div now? No, because now it types wrong. Okay, so how can we fix that now? Right, then I guess this has to become like a maybe integer. But then like all of that intermediate stuff is wrong. Okay, so I'm not going to continue doing this because like we're just going to like keep fixing things which like create other types of problems. If you want to go on the full journey about like why that's not going to work, read some of these course slides. But the punchline is, okay, screw it. Let's use monads instead and see if this will simplify things. Okay, so if I have a monad, I don't think I still won't be able to return an integer. Maybe integers we're stuck with. But let's see. Okay, so to evaluate a value, still x. Am I losing my mind here? Don't I have to define? Hold on. Am I? No, I'm not losing my mind. Okay. So what does it mean to evaluate this expression? So div expression 1 with expression 2. Okay, so we're going to use a do now, which means I can say something like evaluate expression 1. What do I get back if I evaluate expression 1? What's its type? It's a maybe integer, yeah? Are maybe integers, does that form a monad? So I can do something like this, right? I can extract the x from inside of this. And I can also extract the y from inside of that. Which means I just need to return div x and y. Whoops. Oh, jest. So I should be able to evaluate div val4, val2. Okay, but what's currently not working? Well, okay, let's, what happens if I put nothing in here? The monad should handle that. Oh, no, I can't put it there, sorry. Evaluate nothing. What? Oh, it doesn't take a maybe. Yeah, sorry, I'm not with it today. What is this missing though, in terms of like our evaluations? Yeah, I need to check for 0. So how can I do that? Well, I can use an if expression, right? If y is 0, then return 0, else return div x over y. So I should be able to say something like evaluate div val2, val0. Oh, sorry. Just nothing. Yeah. I know. Only nothing. There we go. Let's see what happens. So this is a sub-expression which fails, right? So let's try to evaluate dividing like 7 by the result of that. And this is where things get tricky, right? Because you don't know that this expression is going to fail until like this gets evaluated, which is like the last thing that happens. Right there, like the monad just sorts that out for us. And so the nothings get carried up. That's clean, right? You should think now like, oh, okay, this really would have simplified assignment 2. So one of your homework exercises, you should refactor it just to use a monad. Okay, let's keep going. So yeah, if you want to go on this full adventure of how like it won't work, just go through this. But now I have to show you the rule set for this. Now, maybe I'll ask you to prove one of these, but I'm not actually that interested in having you prove things or monads. They can get kind of complicated. I think the most I'll ask you to do on your homework this week is to prove something isn't applicative, which already is a little bit troubling. But here you go. So in order for something to be an instance of a monad class, these are the things that it has to satisfy, or the data type has to satisfy. You have to provide this return function, which is the same thing as pure, which is just telling me, if I give you A, how do you get structure over that A? You have to provide to me this bind operation with this funny type signature, but effectively it's just saying, give me something with structure in it and like force it into this funny function, right? Where something with structure over B is going to come out. And in addition to defining these, you also have to satisfy the following rules regarding monads. So something called left identity. That is, if you want to return X and like bind that into F, you get F of X. If you take MX and you bind that into return, you just get MX back. That is like stripping something of structure and then putting the structure back, right? Leaves the thing invariant. And then this expression, which I'm not even really going to read through regarding like the associativity. So this third one, I'm going to show you like this. So this is taken from the Haskell's wiki. This monad page is really informative if you wanted to go read it. But effectively, these are the 3 rules for monads displayed, like sort of described as how it would, like what's the downstream effect of actually defining something with a do notation, right? So the left identity means that this do expression is equivalent to this do expression. So, and we can read through it. So like do the following: put structure over X and then reach into that structure and grab X and then apply F to it. Okay, yeah, that these should be the same, right? Because this doesn't actually do anything to X. Right identity, okay, do pull something out of M and then, so it's like reach into the structure of M and pull what's inside and then put M structure back. Right, so obviously that doesn't do anything to M. It's like take the list brackets off and then put the list brackets back on. And then this rule regarding associativity, which essentially is just a rule talking about the order of embedding doesn't really matter. Right? If you do something and then do the next thing, you can swap those. So I don't think I'm never going to ask you to do something to prove associativity, but it is possible, right? Because I just need to give you all of the rules for what the monad is. Don't take a break yet, because I thought I actually did have an example of something's the actual definition of the monad. could, or maybe it's on the next one. Really am losing my mind today. Did you guys want a break or just want to be out a little bit early? Yes, sir. Mm-hmm.
Is that like, because obviously pivot is very like the same signature as that.
It's the same thing. It's return and pure could be, return can be replaced by pure in all cases. Yep. We don't even need it. You could, but like, I don't know. I wouldn't think that that would be possible because like, how could you put something into your structure different ways? Like maybe it's possible, but I don't think it is. So Haskell has, for most of, like for all of its built-in data types, it has a built-in monad applicative functor, if such thing can exist. The one for list is like super strange. I'm going to have you do a different one for your homework. So it is the case that like multiple monad functor or applicative instances can exist for some data type, and that you only are allowed to use one at a time. Right? Like when you load that into Haskell, maybe I'm like really surprised it didn't write a custom instance of a monad, or at least look at one. Maybe I'll rectify that and I'll write a little thing on the ed stem. We could look at one. Okay, let me think. Maybe monad Haskell. If I can find it, I'll just have to share this with the screen. I could have sworn that there was something there. Okay. 1 second, chat. I just have to share something else. Okay, so here is the monad for maybe. So you're asking, or you're asking for either, but it's effectively the same thing. It's like, so what does it mean to return for the maybe monad? Well, just put jest over it. And what does it mean to bind? So you give me something that's maybe A, and you give me a function G, which goes from A to maybe B. And if M is nothing, just return nothing. And otherwise, jest of X goes to G of X. Right, so this is what we always will have a case like this for monads, where the error is just pushed up the chain. And so let's look up the one for either, and I'm certain it'll be the same thing. Either monad Haskell. Where is it? I just want to see it. Okay, do it from here. Either. Monad. It's a bummer. Okay, well, we had the one for at least, we could probably try to write it. Do you want to try to write it in the next 5 minutes for either? It shouldn't be too hard. Yeah. Yeah, that was actually a homework exercise that I gave. But you're still going to be returning like a list of errors. So like that's going to be the thing on the left, like list of error, and like list of errors will get pushed up. But I guess you're saying you want to like concatenate like the error at this level. Yeah, but there's usually like a root error, right? That like is like the central error, which is triggering all the errors upstream. And now you're talking about compilers and stuff like that. But I'm happy just to lift like one error through a system that we declared functionally pure, right? Like that itself is a huge accomplishment. We'll let error handling be the concern of imperative programming. Okay. So we need to take either A or B. Is that how the data type worked, if I recall? Yeah, left A or right B. So either A, B. So if I want to return X, I just want to do something like right of B. Okay, so now it's not, so it's either A, B. And then this is the tough one. Do I take left or right? So I guess it would be something from here to, you know what? No, I'm not going to do this. Just live coding. Like it'd be good to think about this at home because you have to make decisions here, right? Like obviously I don't want to map over the error. That's not going to be very useful. But like we're going to have a case here where it's going to be like left of anything is just left of anything. Like that pushes the thing up the chain. Anyway, okay, let's go to the next stuff. Yeah, sorry, as I said, I'm a little bit off. Being constantly ill is not what I anticipated having a child would be like. You play this fun game where you trade like a quarter of your income to send your child to a daycare. It says, thanks for a quarter of your income. Now here's the plague visited upon you every week. Okay. The state monad. So we talked about now we have a new class. And instances of those class provide to us this binding or do notation. I want to introduce like a very specific monad now called the state monad. And what this is going to do is help us abstract away something that we've been doing up until this point. So you know these tail recursions that we've been doing, you know, we're sort of cheating, right? I'm saying we're not allowed to hold state, but what we can do is like hack state into like the function arguments. And as long as your function, like what was our tail recursions doing? They're given a bunch of like inputs, state, manipulating those inputs and like going to a different state, right? So like a tail recursion is kind of like a state transformation or like a finite state machine. This notion that like any function can have auxiliary variables, which are just being modified, right, to hold state is something that we're going to do often. And in fact, we should abstract that away because like having to thread all of these states through like all of your function calls can get a little bit crazy. So let's talk about that. So suppose I give you a binary tree with value only in its leaves. And I say, I want you to relabel this tree in such a way that like every leaf has a unique label, kind of like your blockus, right? Blockus was easy up until the point that the tile numbers had to be uniquely identified. What would have been useful in that instance? Suppose in that instance for blockus, I gave you a function and that all that function did was like give you new integers that were like guaranteed to be different every time you called that function. Would that have helped you with that blockus homework? How could we accomplish this in the imperative paradigm? What is a function that can just keep returning just like the next number? Huh? Yeah, effectively what we need is like a global variable. So we could have something like an object which had internal state. The best answer I was looking for was yield. You know how you can have functions in Python yield, right? It's like you can break out of the function early and it will remember its state. But effectively all we need is like a global variable. So these are what these state transformations are going to allow us to simulate essentially. So let's try to solve this problem. So here's a tree. And again, it's just values in its leaves. And then otherwise it's a left tree and a right tree. So I want to be able to take something like this, right? So here's a tree with just like 3 nodes with the values A, B, and C. And I want to be able to say label this so I get back nodes labeled 0, 1, and 2. So we can do this with a helper function. So we just sort of, in addition to giving label the tree, like we have to say, here's the number that you should use, right? That was one of the strategies for blockus. tile, but like with these tile numbers. So we're going to do the same type of strategy here. I'm going to say label, but I'm going to tell you what label to use as like part of the input. Okay, so in addition to labels, inputs and outputs, we need some type of helper function which takes auxiliary variables. And these auxiliary variables are going to be, so give me the tree, give me the label you want to use, and I'm going to give back to you the partially labeled tree and the next number that you should use. Right, so we're going to talk about generalizing our function so that they return the thing that they return and also the next state, right, that you should be utilizing. So all our functions are going to take x and state and return y and a new state, right? So we're going to be threading state changes through all of our function calls. So here's how we can do this problem. So here's my helper function. Maybe we should just code this up. Okay, I'll code it up. Let me just grab this. So there is a tree. Let's create a tree. Let's just take the one from the slides, this one. Tree. Oh, we don't have label yet. So there's our tree. Let's load this in. Lead, leaf. Oh my God, how many times can I misspell leaf in one try? Okay. So there's T. There's our function. So we want to do something called helper label. This helper label is going to take a tree of A, and we're going to return a tree of integer values. But I also want to take an integer, which is going to be like the fresh integer. Okay, so it's something like H label. So it's a node, tree left, tree right, and that's going to be equal to something. And this is our fresh integer. The base case is easy. So how do we label a leaf with this fresh integer? Tree, Lord, I'm losing my mind. Tree of A and integer. That should be like this. Okay. So I'm taking a tree of A and a fresh integer, and I'm going to return a tree of A and the next integer to use. So if we come down here to the base case, yeah. Oh, that wasn't a question. Oh, yes. Thank you. Thank you. Yeah. Keep on me today because I'm crashing. Geez, my afternoon lecture is going to be a disaster. Yeah. Tree. Oh, yes, you're correct. Tree of integer. Okay. So how do I relabel this one? This just becomes the leaf of fresh. And I'll just like increment this by 1. So let's think about like the base case. You're saying here is just a tree. It's leaf of 1. And I want you to, it's leaf of A. And I want you to label with 0. So I'm saying, okay, here's leaf of 0, 1, which is like the next fresh integer that you should use. Okay, that was the easy part. Here's the hard part. So let's immediately put in a where clause. So I'm going to want a new left tree, and I'm going to want a new right tree by making a recursive call, but if I'm recursive calling, I'm actually getting a tuple back where this is going to be some type of fresh integer. I'll call it n prime. This is going to be a new fresh integer. Okay, so, but like, how do I reassemble? Because we have to be really careful in the order that we call these things. It's like, what do I want to return? Somehow I want to return I want to reconnect like what we just relabeled. But I also need to return some what's the next label. So we have to be really careful here of like how we thread this state through. So I'm going to H label the left with this fresh number. So it's going to do its thing. And like it may need like 7 fresh numbers, right? This thing here may increment 7 times. Then it comes out to here. And then I can say, okay, go then take that and then label the right tree with this, right? Starting from here. And then you're going to go in and come out and then give me back this as the next starting number. I guess that was one too many brackets. Okay, so first let's see if this works and then we'll try to break it. Okay, so let's try to H label this tree starting from 0. Aha. Oh, wait. I have to take first out of this. Yeah. Right. Because we have something like label is just take the first thing off of this out of the tuple. I don't care about like this is they're saying here like this is the next fresh integer that you should use out of this tree. Okay, but why wouldn't have this worked? Fresh. Well, I'm saying, okay, so you reconstruct the next number you use is the same one that you gave me. Like the state never moved. And that's the problem with this one. Here, I'm telling both of these late trees to start labeling, both starting from 1. Like that can't work either, right? So this issue of having to thread the state like this, right? Like this has to pull out a state, which goes to the next one. And if I had more subcalls, I'd have to do more. I want to abstract this away. This is messy. So that's what we're going to be doing with these state transformations. Okay, so that's what we just talked about. So the notion of holding a state can and should be abstracted away, right? This threading is going to get hard. We expect to use it again and again. We want a state transformation data type. So I basically want to say, you give me any function and I'm going to like decorate it. And I'm going to make that function a state transformation, which means in addition to returning its output and expecting input, it's going to expect a state in addition to its input, and it's going to return its output in a new state. Right? So we'll just be taking in tuples and pushing back tuples. And if we can create this state transformation data type in such a way that it's also a monad, then we can like use the do notation in order to make this stuff easier. So here's our wish list. Suppose I could make fresh the state transformer that we desire, and fresh is a monad. Then I would be able to do the following instead of this like state threading that I was doing before. What would it mean to label a leaf? Well, it means give me a fresh integer and then return leaf of that fresh integer. What does it mean to label the left and right trees with fresh integers? Well, I'm saying label the left tree, pull it out, label the right tree, pull it out, and reconstruct them. See, like the state threading is gone, right? The only place we ever need to actually use an integer is like in the base case, right? But hidden by this monad is like the passing of these tuples, right? So I'm going to show you how we can make a state transformer for a, like given a type, turn that type into a state transformation over that type, and then show you how we can turn that into an instance of a functor, applicative, and monad so that do stuff will work. And we're going to do so mostly by drawing pictures. Now, these pictures are straight from Hutton's book, but I'm not sure Hutton gets to like be the one who claims he invented these things. So this is a very standard way of writing functions. So this is the most trivial picture that I can talk about state transformers. So this thing in the middle is a state transformer. And what does it do? Well, it transforms state. So state goes in on the left, new state comes out on the right. What happens here? I don't care, it's abstracted. right? Someone else will sort that out. At this level of abstraction, I just care that given a state, I get a new state. Okay, so that's the basic state transformer. Upping our game a little bit. So not only do I want these state transformers to like return a new state given an input state, I also want to return output. So now I'm just going to say a state transformer takes state and returns output and a new state. Okay, but like what output does it return? What is the Y? Well, okay, it's the output given this X. So this is a fully fledged state transformer. What I want is a function f that takes X to Y. To turn that into a state transformation, you have to give it, so this is how sort of this works in order of evaluation. You give X and you get back a state transformer. That given S returns Y, which is f of X, and the new state. But that order matters, right? This doesn't become a state transformer until X is given, right? Because it needs to know what Y it's outputting. And the Y is typically f of X. And so we have an input X, state S, an output Y, and an updated state S prime, right? So this is basically what we just did with the tree example. Like X was the tree, S was the fresh integer. And then we got out the relabeled tree and the next fresh integer that we should be using. We're just trying to abstract it. Is there any questions about this? Because now I'm just going to start connecting them. So it's like really important that like you understand how this is working. You sure? I can give you a pop quiz on how to form the applicative for this state transformer. Because every year this is sort of like my class tells me this is the hardest thing. So I really want to make sure that we're understood. So is it really, this is really clear? No one really wants to ask me a question. As soon as one person does, usually the floodgates open. Okay. So these state transformers are just functions. So all we do in Haskell is function composition effectively. So it shouldn't be a surprise to you that I can take two state transformers and like combine them to get a new state transformer. So this is how you combine two state transformers into like another state transformer. So let's look inside here. We have state transformer 1, which, so give me X and I will give you a state transformer 1, which given a state S will give you back output Y, which is f of X, and a new state S prime. Give that Y to here, and I will give you a state transformer 2, which is going to accept S prime, a state, and return Z, which is G of Y, and S double prime, which is like the new state. That, when you combine this, becomes a new state transformer. Like the whole thing can be regarded now as a state transformer that given X returns a state transformer of what's happening in the box. And then given S returns Z, which is G composed with F at X, right? Because F of X gives you Y, G of Y gives you Z, right? So we sort of had a function composition along the top. And given S, you get S double prime. So actually like there is an intermediate state change here, but we don't care. And it's sort of been abstracted away. Right, but so again, give me input, I give you state transformer, give me state, and I give you output in the next state. Okay, so we have state, we have function composition, we're making our way to monads, right? So like, what's the next thing that I want? A monad also has to be a applicative. And in order to be an applicative, you have to be a functor. Okay, so what do you think I need to show you the state transformer is? A functor. So let's think about how we can make a functor over this. So what does a functor do? It was a structure preserving operation. So I'm like saying, here's something with structure. Our structure in this case is like this state transformer wrapper. Here's a function. What should I do? Well, how should I like glue those two things together? Let's go back to like this one, because it's going to be some complication made over this. What does it mean to be given this and a function? All right, so first of all, is the function going to apply for over X or over S? That was a trick question, right? We're going to be applying it to Y, aren't we? Functors don't generally work over input. It's like I give you output, right? So yeah, so I'm going to give you F, and it's going to have to change this Y somehow. So I think I just have to stick like F here, right? So when it comes out, it like goes through the thing that you want to functor, and you get out. So here's the picture. Wait, did I jump the gun a bit? Okay, I did jump the gun, but we'll go to that picture just so I can finish my thought. So here's the functor for the state transformer, where the thing that comes out, you just put G over it now. And we can actually define it like this. In order to define it like this, I have to take a couple steps back. So let's now try to program this, like these pictures. So here's a state type. And for simplicity, like the state can be anything we want it to be. But for simplicity, let's just assume that we're always passing in and out integers. Because then that means, okay, we basically can be passing around anything that's enumerable. Just like give me a hash table and we'll work through it. So our state is always going to be integer state, right? So you can, which works really well with like the Turing machine model anyways, because you can number all of the states that you want to be in. A state transformer then over some type A is, so give me a type A, and in order to make that a state transformer, I need to give you a function which given state gives you back outputs in the next state. So this is like the left-hand side of the box. This is like the right-hand side of the box. So how could our fresh function be implemented as a state transformer? Well, given state 0, what do I want to get back? Well, the thing I want to get back is the output, which in this case is going to be 1, and the new state, which is also going to be 1 in this case. So here's how the state transformer would work for state. This is the most simple type. So fresh state is just going to be take 0 and return the tuple 0, 1. So 0 goes into here, 1 goes into here. Then I say fresh of state prime. And so this is going to return 1 and 2. So 1 goes into here and 2 goes into there. Fresh of state double prime. Well, this is 1. So fresh of state double prime is going to return a tuple 2 and 3. So if we look at this, we indeed get 0, 1, and 2. And state triple prime is holding 3. Right? So this is how like the state transformer can actually like work in action. And it's this sort of that we want to generalize, right? Because I don't care like just how complicated this is, as long as we have any function which has a tuple that's returning like X and S prime. Okay, so let's try to see if we can code that. So unfortunately, types declared using type cannot be made instances of classes. So we have to use this new type declaration, which means we have to use this dummy constructor. And these dummy constructors are a pain in our asses because it always means we have to do pattern matching in and out of them in order to do anything, but it just is what it is. In order to mitigate this, I'm going to create this function called apply, which given a state transformer over A and a state gives you back the tuple A in state. So it's effectively just allowing me to apply the state transformation to input without like, and it's handling all of the pattern matching in it, right? So to apply this state to this state transformer with this sort of dummy constructor in front of it is equal to taking states and putting it into the state transformer. So ST is something, again, which is going to take state and return output and a new state. So here's the functor, and this is how we can describe it. Right? So you're going to give me a state transformation, right? And why is there no X here? Because remember what I said, you have to give input and you get a state transformer back, right? So that I didn't put X there means like this has already been done. The state transformer has already been built. It knows that it's returning X. So all it needs to do is take S and return X and S prime. That's like the original state transformer. So yes. Oh, it's the same thing as where. So I've been using where this whole time. That's my preference. But let is where, but it's before. So you can always say let X equals 2 in Y times X. Or you can say Y times X where X is equal to 2. Now I'm going to have to start using lets because it's the only way to use to make this type of simplification while inside the definition of a function. I tried to do wheres in my first year and I ended up screwing everything up actually. But let's just read through this and perhaps it will make sense, right? So you're going to give me a state transformer and a function. I need to return to you a new state transformer. Okay, so that's why this dummy variable is here, right? Because all the state transformers need to be decorated with this dummy decorator. So you can just ignore it. So what is a state transformer? Well, it's something that takes state and returns a tuple where the tuple is going to be what? Well, here I want it to be GX S prime. So here's the GX, here's the S prime. But what is GX? Well, I need to get this X out of this state transformer, which means I have to put S into here in order to get this out. Does that make sense? So I apply to the state transformer S. It gives me back X and S prime, this. Which then I just need to return GX and S prime. So this is the functor definition for a state transformation. And it's so generic, like we didn't talk about what X is or what any of these functions are, but it could work over our fresh, for example, right? We could triple all of the numbers coming out of our fresh if we wanted. Does this make sense? Because the next one's the applicative, which barely even makes sense to me, right? So let's do the applicative. Half of it's easy, right? What does it mean to like be pure? What does it mean to be brought into the structure? Well, it's just if you give me X and you give me S, what's the simplest state transformer that I can give you? Well, okay, so I'm saying here's X, build me a state transformer. I'm saying, okay, I'm going to build you a state transformer that always returns X and never changes state, right? That's the simplest structure that we could possibly give to anything that's not already a state transformer. This does nothing essentially except go in a big circle. But here it is, right? What does it mean to put X into structure? It means to build a state transformer. So there's the dummy constructor that takes a state S and returns a tuple XS, right? Remember, a state transformer is any function that's given state returns a tuple, right? Which have output in the next state. This is the definition of applicative for a state transformer. Let's not dwell on it because like the applicative functor is kind of weird in that it's like an intermediary between like functors and monads, and the monad is the thing that we actually want, but since the monad needs this applicative, but we can understand the picture nonetheless, right? So an applicative is something that operates over two state transformers, right? So you want to say state transformer A, I have a state transformer B, I have a state transformer which is like inside of it is some function. So what does this mean? So take a state transformer for F and a state transformation for X. So given S, this is going to spit out F and S prime. Right, so give S to the state transformer for F and you're going to get F and S prime. If you put S prime into the state transformer for X, you're going to get out X and S double prime. So there's X and S double prime. What do I ultimately want to return? Well, F of X, S double prime. So that's what this is, right? And this is where we're using the functor. Right, so you draw the big box around here, you get a new state transformer, and that's what it means to be an applicative. It's not overly necessary to like engage with this too much, but you should be able to like understand that like this code is implementing like this picture. Savvy? Okay. Here's the monad for the state transformation, and it's much more straightforward than the applicative, right? So what does it mean to bind in a state transformation? Well, you need to give me a state transformer encapsulating A, then a function which gives me A and gives me a state transformer over B, and then I'll give you a state transformer over B. So remember, this is the input. Here's a state transformation over A. It's already built, right? So there is no X. That's already been done. So I have something that given state returns tuple X and S prime. I need a function that given A returns a state transformer over B. So give me A, I'll give you a state transformer over B. That would be, where is it? Yeah, here. That's what the F is, right? So given X, it gives you a state transformer over B, which is expecting to take this input here, S prime. I know this gets kind of tricky. So F of X does what, right? It takes A and returns a state transformation over B. This S prime goes into that state transform over B and gives you a state transform over B. It's just basically what this picture is doing. So you'll have to go home. You have to sort of dwell on this for a bit. But it's the case we really haven't studied the monad or applicative or functor for any data type like really, really carefully. I just need this for next week because I'm going to say IO is a state transformation, and spoiler alert, over everything, right? The state that you have to give IO is the position of every atom in the universe. And then I can purely do IO, but then I have to update you of like what the state change of the universe is. The idea being, if you want me to do IO purely, and you tell me what the position of every atom is in the universe, I can do it purely, but only if I have that information. We'll talk about this next week, but like, do we have access to the position of every atom in the universe? No, but since we'll never have to pattern match out of this, since I can just do state transformations by jumping inside the state transformation, it's not going to matter. It's pretty damn neat. Okay. So let's do this tree relabeling with applicatives and with the monads now that we built them. So how can we do that? So here's our fresh state transformer. And so all the state transformer is this dummy constructor. Given state, I'm going to return to you a fresh integer and also the new state. And so this is just a little bit trivial, right? Because the fresh integers that we're returning and the new state that we're going to are sort of both integers. Right? But again, give me state and I'll give you output in the new state. This is how we can label the tree using a functor effectively, right? Maybe I can just do this here. So here is our H label where we were threading through the state ourselves. So now I'm saying I can take this out. Right? That's something that's going to be hidden away. So it's something like I want a state transformation over, geez, am I losing my mind? Yeah, I give you a tree over A and you get a state transformation over tree int. Yeah, I don't think I'm well enough to do this off the cuff, so I'll just stick to the slides. I'm really going down. Okay, so we have a tree A and a state transformation over tree of integer, right? So we just want to take this tree and like give it fresh labels. So how does this work? Well, the base case is a leaf, and I'm just going to take this leaf and I'm going to map it to the fresh integer. Now, does the order here make sense? Don't we usually map functions over things? Leaf is a function, right? That's like expecting a value to put leaf over. So fresh is a state transformation that's going to return to us a fresh integer. But it's in the first position. But who cares? The functor handles that for us. Like, we know abstractly how to map over state transformers because we've defined it to be that way. And we're going to map over what? The first thing. I drew the picture, right? Right. So if we go back to the picture, just imagine G is leaf. So what you're going to get out of here is like leaf of X and the new state to use. So this is going to just apply leaf to some fresh integer. For the recursion, I have a node, I have a left tree and a right tree. And what do I want to return? Well, I want to label the right tree. I want to label the left tree. And then I want to like put node over those two things. But since all of these things are state transformers, I'm limited to using my functors and applicatives. Otherwise, I have to do a bunch of pattern matching in and out of these tuples. Right? But it's been set up so that I can say, go get me the right tree, go get me the left tree, and then apply node over it. Okay, so this is called the applicative form. Some Haskell programmers prefer this, but I'll show you what it looks like when we're using like do's. Maybe that'll be more clear. So here it is using the state monad. So now I have a state transformer, which automatically like is a monad. And so given any data type, I can have a state transformation over that data type and use binding. So how do I label a leaf? Well, it's do the following things. Extract a fresh integer and return leaf of that fresh integer. Okay, that's the base case. How do I do it for the recursive case now? How do I label a node which has a left tree and a right tree? Well, do the following things. Label the left tree, but that's a state transformation now, but I don't care. Reach in and grab me the tree. That's the thing that I want, like the left tree. Now label the right, but you're a state transformation, but I don't care. Just reach in and grab me the right tree. Recombine them like this and return. Put it back in a state transformation. Right. So what we're like, this is actually like if you go back to the original function I wrote, which was like manually threading the state through, this monad automates that now, right? It's just passing the state through and the state's no longer even visible to us at this level because it's been abstracted away. The other benefit here as well is that any of these functions the sub-computations can fail, right? And it's going to lift that up automatically. Any questions regarding this? Is always the toughest lecture. So, after next week's lecture, that's like we're content finished effectively in terms of your exam and your assessments. So next week is IO. The week after that, I'm going to show parsing because parsing is really elegant in Haskell, but I'm not going to test you on parsing or give you an assignment. So after next week, you could basically skip the rest of the classes and not miss any content for exams. But I'm still going to try to give you some value on those things. And then the last lecture, I'm going to sort of do a review of everything that we did and then show you how to like port it all to Python. And not all of it, but like a lot of it, right? Because remember, I'm not trying to make any of you Haskell programmers. I'm just trying to demonstrate to you that recursion is a powerful tool that you shouldn't be afraid of. So you guys getting more used to recursion now that you've like are literally like, there is no other alternative way of solving these problems to think about it inductively. So good. If like you come out of here reaching for the recursion tool more closely, I'll be happy. Okay, so you can look at this at home. So for some homework, you can try to prove that the state monads satisfy functor, applicative, and monad laws, but don't try too hard. Like these are going to be really hectic proofs. So just play a little bit just to get some sense of how you would do it. So like next week, hello world, right? We've been building this all week. And round 2 of the NHL playoffs start tomorrow. Right? New Jersey and New York are just deciding who gets to go to the second round. But I'll give you all 7s too if the Maple Leafs win the cup. Yeah, you just need to find a witch to lift the curse and then some type of time machine, right, to move the playoffs earlier. Okay, so welcome back, everyone. I'll see you later. We'll get marking on those assignments soon. Bye, chat. See you later. Bye-bye, everyone.